Great, we're all here. I hope we dodge what's going around. I mean, that's to say, I hope it's not coming around. It's great to be back in this slot. SPLV is still alive, and remarkably, so am I. I mean, you know, 5 years ago, I was already experiencing quite significant heart symptoms during SPLV 2019, which got worse and worse over the next few weeks. And I eventually went splat. So I'm going to try not to have too wild a time. But anyway, I brought a computer so that I can read the picture of my notes, which I foolishly put on a whiteboard that's attached to the wall of my study. So finding a movable object to write your notes on. So I've also sent them around on the Zulip by way of generating some noise. I've got a story to tell you. It's all about types. And if it's true, and I think it is, you folks are going to need a whole new organization. And if you get that reference, you're doing well. Anyway, so I've got 3 lectures. I'm going to talk in this lecture about definitions, about how we write down some, how we write down the rules of a type theory, and how we convince ourselves that those rules might make some sort of sense. I'm going to tell you things that flatly contradict every available textbook. That's, but, we're hosting. My heresies are your problem. Anyway, then this afternoon, I'm going to try and prove some theorems about the type theory that I'm going to set up this morning. And I'm hoping that various of the eccentricities in my mode of definition that I, in this morning's setup, pay off this afternoon when I try and prove some theorems about type theory, doing as little work as possible. What was it Andy Pitts likes to say? Type preservation theorems are 2 a penny. Well, I think they're cheaper than that. Let's see what we can do. And then hopefully tomorrow I might even use a computer, because there's no point in having a cunning mode of definition that leads to cheap proofs if you can't bully it into your theorem prover of choice. So there might actually be some Agda tomorrow, if I can find it. You can see on my 3rd panel, I'm saying, do the St Andrews SPLS talk more slowly and with words. So some of you who may have been at the silent talk that I gave, where I just operated machinery and proved an inscrutable theorem. I should probably not cook it that way tomorrow. Got a little bit more time, so there could be some words. All right, I am going to start, hopefully straightforwardly, warming up to some of the ideas with the simply typed lambda calculus. Let's let's figure out how to cook that. I realize experience levels in this room are likely to be quite diverse. I'm doing a core module I want to bring everyone with. I will try and be clear enough for the people with less experience and weird enough for the people with more. Okay, first up, I'm going to write down, I'm going to explain the rules of the simply typed lambda calculus, which means we need the ingredients that rules are made from. Rules are made from judgments. Just go for it, Dylan. And the most important thing about judgments is that we specify a whole bunch of stuff by writing things in rectangles. I was taught in Edinburgh, and that means I draw rectangles. And in them, I write judgment forms that look like this. Going to use red sometimes. So this symbol is pronounced ni, because this symbol is pronounced in. And you can do all the Monty Python you like. Yes. So I'm going to present the simply typed lambda calculus in an explicitly bidirectional manner. So sometimes types are proposed in advance and we check things with respect to them. Sometimes terms arrive first and we figure out what type they are by looking them up. So I should already have written down a little grammar. Maybe I'll do that on a different piece of paper and hide it afterwards. Right, so there are going to be types, which are going to be good to write down your Fortran conventions. There's going to be base type, which is not going to be interesting. And then there are going to be types. And sigma and tau are going to be types, and are going to be simple types. And then there are going to be checkable terms, which I'll use letters late in the alphabet. And they will include lambda terms, but also I shall embed synthesizable terms. And then the synthesizable terms include applications, variables, and radicals. I call these things radicals. These are terms with a type annotation. So this is the situation here. Well, you'll see in a moment. You should expect, if you're type checking a term that you can synthesize a type for, then you have a potential problem, which is too many opinions about the type of the thing. Whereas if you're trying to synthesize a type of a term that can only be type checked, you've got no chance unless you're a very good guesser like Robin Milner, or somebody writes a type annotation. Okay, so that's the grammar that we're working with. Let's, yes? The line under the E is simply to have some sort of mark to show that I'm embedding something from this syntax into that syntax. On a computer, I wouldn't write, I would make sure that was empty syntax. But when I'm doing meta theory, I want to see when that's happening. Okay, so various people have various philosophies of bidirectional type checking. Some people use the directions to manage types of different polarities, where people think about positive types as being defined by how you make things, and negative types defined by how you use things. And there's a perfectly respectable school of bidirectional type checking, which aligns with polarity. I'm not one of those people, but I respect that point of view. I use type checking for introduction forms and type synthesis for elimination forms. Okay, so I'm going to write a lot of rules down, and a rule looks like a horizontal line with a conclusion that goes underneath the line. For example, that a function type accepts a function. Note, I'm not writing type annotations on my function. I mentioned that earlier. So I want to say that a type, if it happens to be a function type, will accept a lambda term under certain conditions. And the conditions that have to hold for this to be true, I write above the line. And I'm going to write a turnstile here, a little x there. At some point, I will get fed up trying to keep things color-coded. But for now, it's important. Right. So to see if a type accepts a lambda term, first check it's a function type, split it apart into the pieces, make a hypothetical judgment that the variable, which stands for the input of the function, happens to belong to the domain of the function type, and then check that the body of the function lives in the codomain. So one reason I'm doing this by hand slowly in a lecture room is so that you can see how the thought process of type checking plays out over time when I write the rules. Okay, so this hypothetical judgment is a way of saying we're kind of locally extending the rules by explaining how to synthesize a type for this particular variable. Right, here's where I make my customary threat, which is that if anybody hassles me about fresh variables, I shall switch to using de Bruijn indices. I'll be fine, you won't. Right. So actually, yes?
I'm not fast enough. So, okay. So now you have a context on the left from the turnstile in your premise, but no context in the conclusion. Are you just...
This is an excellent question, and one which I was going to answer later, but I'll come to it now. You notice correctly that I have not written any contexts. This is not a context, it's a context extension. It explains what has changed, but I'm leaving the ambient notion of what's available entirely implicit. And there's a reason why I'm doing that, and the reason is this. The first rule of Stability Under Substitution Club is that you do not talk about free variables. What do substitutions affect? Substitutions barrel through the rest of terms and hit only the free variables. So if you never talk about free variables, you can never say something which is falsified by the action of a substitution. That's why I only ever talk about rules which occur, or about variables which occur in bound in the syntax I'm working with. So I only locally extend the context here. I don't talk about the global context of variables that are already free in case I say something stupid about them. So yeah, there is a context, it's implicit, it's being threaded effectively. But one of my objectives here is to make sure that stability under substitution is not something you prove. It's something you don't fuck up. Oh, yes.
If I were Martin Hyland at this point, would I be suggesting that
Yeah, it's live.
that there's some kind of ambient, not quite a topos necessarily, but something there that only allows basically what you just said, but in fancy schmancy categorical language. Is that explicitly inside your mind, even if you didn't put it in that language?
Probably. I'm certainly thinking, I mean, when I work with these things, I'm always working with, formalizing these things, I'm always working with explicitly scoped terms. Indeed, what's more, I'm always extremely aware of not only the scope of terms, but their support.
So you're
yes.
working inside a logic in which you can't fuck substitution up because every predicate is invariant under this explicit substitution action.
Yes, that's exactly the plan.
Martha, thank you.
Okay, let's have a rule on the other side. Let's do application. So we're trying to figure out the type of some function application. How do we do it? Well, let's figure out the type of the function because it's synthesizable. And then check that it's a function type. And now we found out that it's a function type. We can check the argument. And we can also give back the codomain of the function type as the return type of the application. Okay, so we've got a couple of rules there. I'm not going to write down a variable rule because I've got hypothetical judgments. That's to say, variable rules are always hypothetical. If there aren't any variables in scope, there aren't any variable rules. Each variable gets its own rule. Okie dokie. What I mean is that when I bring a variable into scope, I make a hypothetical judgment, which effectively amounts to a new rule explaining a typing rule for that variable in particular. Namely, that for X, you can synthesize the type sigma in this case. Right. I've done, sorry, yes?
Inference versus check.
Yes, checking gets neat because so one thing I'm always pernickety about is time. I want time to go from left to right. So if the type comes first, the type is written to the left. And if the type comes afterwards, it's written to the right. And I have shamelessly stolen the set theorist's symbol because it has appropriate lack of symmetry in the dimension that I care about. So I can safely write it backwards and notice the difference. So yes, checking synthesis. Right. Checking rule. If we want to check a synthesizable term, we can start by synthesizing its type. And now we've got two candidates for the type of E. They had better agree. Right. Here's a thing to note when I write typing rules. I will never be implicit about requirements that two things which come from different places have to be equal. I will never just use the same variable in two places. I will always insist that two things that come from different sources, when they collide, you know, that you'll see something. You'll see some indication that they have to be the same. And here, this tau comes from whoever asked us to check the type, whereas sigma came from a different source. Sigma was the synthesized type. So there's something honest to goodness to check here. And you can think this equality sign, this equivalence, I really mean syntactic equality here. What can I do here?
Can you cover this reformulation?
Yeah, probably a basic question like, can you elaborate on synthesis? Like, what exactly are you synthesizing? Like, I don't understand.
Well, so when I say synthesis, what I mean is that when we're solving problems like this, somebody proposes a term and we attempt to compute the type of this term. So, so actually this is a point at which I should indicate that as far as I'm concerned, the places in a typing judgment. So here, the ni and the in are just syntax, but these things that are variables are sitting in places, and they are not all the same sort of thing. And that in particular is why some of them are red. This tau is what I call an input. It's the person who wants the judgment to hold specifies which tau they would like to check the term at. This sigma, on the other hand, is an output. Somebody offers a term E and wants to be told the type of it. So you can read a judgment form as a very small interaction protocol in a very simple language of session types. And that tells you how to interact with a typing rule. Because a typing rule is really an actor. And typing derivations are made of lots of instances of typing rules which talk to each other. And the judgment form is the protocol whereby they talk to each other. The red things are neither inputs nor outputs, or rather, in a way, they're both. The red things are what I call the subjects of the judgment. Let me put it this way. Everything that lives in a place in a judgment is some kind of signal. We've just established that judgment forms are interaction protocols. So these are signals. A signal has a sender and a receiver. But a signal also has a guarantor. The whole point is that someone is making a promise about the signal. And I make a distinction between two kinds of signal. I call them citizens and subjects. You can imagine what had just happened when this terminology came into my head. A citizen is a signal whose sender is its guarantor. The person who asks for a type to be checked is responsible for that type even being a type. And the person who synthesizes this type, sigma, is responsible for this type even being a type. There is some sort of promise being made about a signal which is a citizen, and the person who is sending that signal is making that promise. Meanwhile, These things here, the red things, they are mere subjects, and they cannot be trusted. The reason, so that a subject is a signal whose guarantor, if you're lucky, is its receiver. The whole point of asking, does tau check T? The sender doesn't know whether T makes any sense, is making no promises about it, is hoping that whoever is delivering this judgment will make a promise about T. So already, we're just being a little bit more discriminating about what's going on in typing rules. Let me write the last rule down, just to get to the end of this picture. How do we synthesize the type of a thing with a type annotation? Yes? Uh-huh.
Before time checking, like, don't you have term and type like at the same time, sort of?
Yeah. So the question was don't these things show up at the same time? Operationally, yes, they do. To some extent, you have to have checked that the type even makes sense before you can contemplate asking the question. That's my point. So certainly any sort of guarantee about the term happens after the guarantee about the type, even if as a signal it's transmitted at the same time. But okay, so so a funny color thing is about to happen. Which should make you instantly suspicious. So we get a term with a type annotation, and we want to synthesize its type. We've got a pretty good clue for what type we want. We'd better check that the term actually has that type, and then we can give back that very type. But how come my red tau turned into a black tau? That's not normal. That's weird. It's a peculiar property of this language of types that everything which is syntactically a type is semantically a type. So there's nothing to check. So I get, well, yeah, just by parsing, the red tau is a valid black tau. But in more interesting systems, we would have work to do to make sure that the lump of syntax that came in the type position even was a type. So there we go. That's the simply typed lambda calculus cooked bidirectionally, and I'm just trying to remember all the things I meant to say. Many of you have been kind enough to provoke them already. Yes, so one thing I need to say is a rule is you should think of as it being a server for its conclusion and a client for its premises. So essentially, you know, if I'm checking this function, right, you know, if I'm the rule, I'm being asked, does this lambda term check at this function type? And I, in turn, I'm going to ask whether the body of the function type checks appropriately. So I'm going to be the client for the sub-goal. And when you think in those terms and you understand the way that judgment forms behave like interaction protocols, then you can see that what's really happening is that we're building a kind of tree of concurrent communicating type checking processes, Or as I said to myself in 2003, fuck me, I'm writing an operating system. That was a key realization in building a dependent type checker. What else do I need to say? Oh, some useful stuff, some really important stuff, actually. So these things, the sigma and the tau and the t and the s and the f, all of these things are referred to as schematic variables. They stand for actual stuff in actual type checking problems. And if you've seen this kind of rule before, you're used to the schematic variables being implicitly universally quantified, kind of off stage. The variables are bound by some hidden for alls, and every explicit occurrence in the rule is a use site of the variable. And the idea is that that any valid instance of the variable, the rule holds for any substitution instance of the schematic variables. Well, that's not quite the way I'm cooking it anymore. Because now that we've got a notion of information flow and inputs and outputs, we can instead classify one occurrence of each schematic variable as a binding occurrence and all the rest as use sites. Because here's the deal. In the conclusion of a rule, I write patterns in input positions. I'm the receiver of this type, and I'm pattern matching on it to see that it is a function type, sigma arrow tau. Whereas in premises, the inputs are meta expressions. So this sigma is a use site of the pattern variable bound here. This tau is a use site of this pattern variable bound here. Things come from somewhere, they go places. That's one thing we're arranging for, is that every signal has a place it comes from. And when we receive things, we can match them with meta patterns. And when we are building signals to send them, we construct them with meta expressions. And these two notions, patterns and expressions, do not have to be the same. And in fact, we'll see a little bit later on, it's really important that they're different. The kinds of questions we can ask in a pattern are, there's a directionality to them. We can put things together in more interesting ways than we can take things apart, simply because there might be more than one way to take something apart. I'll come back to that. It doesn't really show up here because all we're interested in doing is matching against arrows. Yes?
I might be stepping back a second, but I'm still a little bit confused behind why or how there are no axioms in this system. And I'm trying to build a proof tree in my head, and I can't see where it stops.
There are no global axioms in this system, but there are local hypothetical axioms.
Okay, so
I'll take the bait. Let's actually build a typing derivation for the identity function.
thank you.
Yes.
Much appreciated. Thank you.
Right. Yeah. So somebody wants to type check. Sorry, that iota got away with it. Somebody wants to check lambda x dot x. Right. Lambda x dot embedded x. Okay. So maybe I can just about squidge the rules on. How far? Right. Okay. So, only one game in town, lambda rule. I acquire a hypothetical x is in iota.
Could you put the rows down?
Unfortunately, if I do that, they disappear. I could fold the paper, except I'm going to have to unfold the paper any minute now. Right, so now I have to check. So here, indeed, I will emphasize that went that way. Maybe I should use a different color. It's more noticeably different from red. And then this iota is going to be used to check embedded x. Right. So now I do look. So in deriving this thing, I'm allowed to use this as an axiom. So now you can see it's going to work. Yes. Right. Okay. So now I have to change direction. I have to synthesize a type for x. But fortunately, I now locally have an axiom that tells me that the type of x is iota. And then I have to check that iota is equal to iota. So that was that one. Oh, whoops, I should have used orange for that. Life is full of color errors. Philippa Cowderoy does excellent provenance of variables in these sort of derivations.
What exactly is that equivalent sign, like between two types?
I'm checking that they are syntactically equal.
Syntax.
So nothing weirder than, is it the exact same thing?
Okay. And also, so this notion of this embedded terms. So like, what if I do like lambda x dot x instead of putting that?
It's not syntactically correct.
Yeah, but like, why do you have to define it that way? Like a separate sort of embedded terms. Why?
Right. So I'm separating at the level of the grammar the terms for which I expect a type to be given in advance and the terms for which I expect to synthesize types.
Oh,
right.
Okay, so
Yeah. Right. And there are some subtle things you'll notice. But
So I'd like to get some things off my chest, please. If I may. So first of all, this is amazing, and thank you. And secondly, anytime anyone starts talking about hypotheticals, it's a sign that they're covering something up. You see this between natural deduction and sequence. Could you go back to the other derivation? So I don't believe in hypotheticals. Either something's there or it isn't. So I'm not questioning what you're doing, which I mean is beautiful, but there's something clearly being swept under the carpet here.
yeah.
I have a proposal for what it might be. You're working, but before I say that, I'll just say, this seems to me it's begging for a denotational semantics, some kind of denotational meaning of what the difference is between the underlying terms and the not underlying terms. And I'm not keen on this semi-mystic hand-waving about, look at the beauty of this thing. Yes, it's beautiful, but what's actually happening? I propose you're working in a set theory where there is an explicit substitution over atoms, and in the background, there's some kind of function space, which, being in the theory, has an explicit substitution. That concludes me getting stuff off my chest. Thank you.
I can see you needed to say that. I shan't respond at this time. Jesse.
So clarifying question. So for the hypothetical, should we view that as basically scoping over all the subtrees rooted from the right-hand side of that rule?
Correct.
Okay.
We're constructing a derivation right of the turnstile. This is a context extension. So the question was, should we consider this hypothetical as scoping over this entire judgment? The answer is yes. So that's the point, is that that there is a context. I'm not writing it, but it is there. I'm not writing it in order not to say anything stupid about it. I'm willing to extend it locally with things which are morally fresh. Okay, we're nearly done, except that I want to look back at the grammar and think for a moment about computation. I've said what the terms are. I've said how to type check them, but you know, we quite like running programs. One thing you'll notice is that if I throw away the radicals, I've actually written down the syntax of normal forms, of beta normal forms in the simply typed lambda calculus. You'll notice that the function in an application is in the wrong syntactic category to be a lambda. So there's no way to write down a conventional beta redex in this language. However, once we put the radicals in, something marvelous happens. You can make an application of a radical. So let's write down the reduction rules for this system. I think there's enough room on this piece of paper to do that. Right, first of all, these rules are written in black because only citizens are allowed to compute. Right? That's what being a citizen gives you. Someone's made a guarantee. That guarantee is that computation is going to work. So that's what citizenship buys you. Citizenship is having a denotational semantics. And that's when I say a subject is an input and an output, because when it's a, you know, it comes in as raw syntax, it goes back out to the sender as something meaningful. So, I mean, in some implementations, it literally is that the result of elaboration is a different thing. So let's write down, first of all, the beta rule. So someone gives us a term radicalized at a function type, and that's applied to some argument S, and that steps to T with the bound variable substituted. Can I substitute S? No, I can't, because variables are synthesizable. I have to substitute radicalized S. And can I just give back T? No, because the whole application has to be synthesizable. So I have to radicalize the result. And what you're seeing here is that every beta redex where computation can happen has to be annotated by the type at which computation is happening. It's the being radicalized with a type that enables something to be active in computation. That's why I call it a radical, because it's like a radical in a chemical reaction. It's the type annotation which enables this thing to compute. And what do you notice? That when we substitute actual terms, well, we substitute the radicalized S for the otherwise inert variable X, that radicalized, that radical can now compute. If that X is applied, it's now ready to do something. And likewise, the result of the whole computation is radicalized. So it, I mean, maybe T is also a function and we've got another argument on the right. And what do you notice? Computation at a big type turns into a splatter of computations at strictly smaller types. This is the explanation of cut elimination for this logic right there in your face. So there's a question up at the back there.
Can't claim I'm following everything. Just to clarify, can you explain why the S that you're applying this to is not radical?
Let's get back to the grammar. Variables live in the EF fragment. So this S is a checkable term. It's sitting in an argument position. It cannot be substituted for an X because it's not even in the same syntactic category as X. So variables, they are so basically I'm ensuring that when an inert variable, so you can think of, like when you go to a pub and they give you order some food and they give you a spoon with a number on it. That's not food. But hopefully it will have food substituted for it at some point in the future. All right, don't eat the spoon. So I'm ensuring that when we substitute for the inert variable, we get something which is capable of computation because it's radicalized at a type. That's the positive reason for it. Okay, hands everywhere. Who's going first?
To further your analogy with the actors in communication, would the yes be that a promise?
So
That you receive
Yes.
that then you have to wait.
yeah, and we'd certainly do it that way. So you can actually say, well, we're in a position. I mean, if you're actually building concurrent type checkers, what you end up doing is introducing variables which stand for signals you don't know yet, and hoping they get substituted, so that you can make as much progress as possible.
Yeah. For your beta reduction you defined, maybe you could show it. And so I seem to still have a little bit of a problem with your implicit context. So in your left term of the application, X is not a free variable because it's bound in the term.
Yeah.
So it's your statement about we don't talk about free variables doesn't apply here. So then we reduce it. And now in the term T, X is free. And I can't really see how your substitution then matches X with S. So
this also is an excellent question, but there is method in my madness and vice versa. Of course, the left-hand side is a pattern. These are the binding sites of T and sigma and tau. T is bound in the scope of an X. Correspondingly, if I'm using it outside of the scope of an X, if there is no X capturing T, I have to explain what's going instead of X. So I write this substitution here. I don't even need to write the X because there's only one thing I could possibly be substituting, namely the one variable that was in scope at the binding site of T, but not at the use site of T. So again, once you start thinking in terms of not kind of externally universally quantified variables, that's kind of scope over a whole judgment, but rather thinking of patterns and expressions where the schematic variables have one explicit binding site with particular things in scope there, then this becomes a little bit clearer.
Does it make sense to think of T then as a one
multiple contexts?
No, because there might be multiple occurrences of X in little t. Or none. But what's happening here is that I have to patch over the gap between binding site context and use site context by substituting for everything that's in one but not the other. Yes.
So in this example, the lambda x dot t has a radical, it has a type. So does that mean in this syntax, in this use case, the user is going to have to annotate their lambdas at some top level if they define a top level lambda?
I mean, I should of course make clear that I'm building kind of technology for explicitly typed core languages. But in general, the thing about programming is that we tend, so one thing I haven't got here, I haven't written down any kind of notion of definition. And that's the normal place you would write a type annotation. We don't often actually write beta redexes in programs. We write beta redexes in examples that we want to run, but less so in the text of programs. I mean, I'm not going to argue that the bidirectional story is a complete replacement for unification-based type inference. It really isn't. But it's what's nice here is that if you control tightly the flow of information, then you can see where the types are actually needed. And where they're needed is where computation is about to happen. In order, I mean, you can almost, in fact, you can treat the type as being raw inductive carbohydrate, the actual fuel that makes the computation possible. You know, we're actually eating the arrow to take a computation step. You know, we're burning it. It's like carbohydrate, spud powered computing. What can I do for you?
The conversation, but wouldn't this completely break down if you add letrec to your since you have that?
Well, I wouldn't add letrec to any language. Right. Okay, I need one more rule because this is how you push a cut further in, make the type smaller.
Yeah, no, I also put that rule with E. So you have this on the premise, like you have one of the premise that you have some E and you know that it is of some type sigma. And what do you mean by embedding that E?
That's actually an excellent question, given the thing I'm going to. So you should think of embedding also as kind of saying stop. So what you've got, you notice that all of the things like applications which compute live on the synthesizable side of things. And whereas all the things that sort of sit there being values are on the checking side of things. So that embedding simply says, here's a computation, here's where this computation stops. So the rule that's missing is a thing which takes a radical that is embedded. So this is a radicalized thing which is not being eliminated. It's being taken as a value. It's no longer in a position to compute. We can confiscate its potatoes. Yeah, so this really says, you know, here's where we're splicing in to a value the result of a computation. If that makes sense. So these things go, these things don't go. So this is basically saying the cut has been completely eliminated. We no longer need the type at which cut elimination is happening. Yes.
Correct. The two squiggly lines are now two different relations for the one for the synthesizing, one for the checking.
Yes.
Yeah.
Right. Okay, good. We're an hour in. I've got half an hour, but I've actually told most of the story that I want to tell about the structure of typing rules, typing judgments seen as interaction protocols, typing rules seen as servers for their conclusion and clients for their premises, and pushing the information around and thinking about schematic variables as having a binding site in a pattern and use sites in expressions. So I think we're proper warmed up. Shall we do some dependent type theory?
Oops, one more question, if it's okay. So at first I want to thank you because I never got really warm with bidirectional type checking, and now it makes sense to a really high degree for me, and I see the usefulness. But one question was, when looking into like type theories, we have like 3 questions to ask: type checking, type inference, and the third is type inhabitation. So I see you have answered the first 2, and this makes sense. Have you any idea about the last question of the usefulness of this approach for type inhabitation?
Maybe, although it's, I mean, that problem becomes too hard to solve when it's interesting enough to be useful. But you know, when we're still in the stage of inventing, well, yeah. So I'm thinking of the late great Roy Dekoff and his calculi with intuitionistic proof search, which is basically the type inhabitation problem. And there you do indeed see a separation between proof search moves, which involve a kind of morally right rules, or, you know, building things that have types, and proof search moves, which consist of picking an available hypothesis or picking a variable that's in scope and figuring out how to make use of it to do something. So if you're in the business of constructing cut-free proofs, i.e. proofs with no radicals, then you actually really do see that the type synthesis judgment amounts to the bit of proof search that makes use of a hypothesis. So if you think about, if you don't have any radicals, then every synthesizable term has a free variable in function position and a spine of arguments hanging off it. So it corresponds to appeal to a hypothesis and then doing a bunch of eliminations to that hypothesis to deduce a conclusion. So yeah, there is some structure to proof search in this situation, especially if you don't use radicals and are just looking for proofs, looking for terms in normal forms. Of course, when we go dependent, there's absolutely no chance of doing proof search in any comprehensive way. Okay, well, that was fun. Spending an hour on 3 pieces of paper. Right. So let's move on to type theory. I'm going to throw away the Greek letters because everything's a term. And so we'll have ST, big S, big T. I'll try and kind of use case conventions. And I'm basically going to do the bidirectional version of Martin-Löf's 1971 type theory, which we know is inconsistent. But that's a deliberate hand tied behind my back. Because we need to think about how much computation we can reliably do in a type theory that has unsafe computation. Right, so we'll have types. We'll have function types. We'll have functions. And we'll have embedded things. And as before, we'll have variables, applications, and radicals. Right. So everybody fine with the syntax? Same separation. Yep. Which T? In the pi type? Well, it's in the scope of a binder, and correspondingly, it's implicitly allowed to contain x's, right? If I wanted to say that x could not appear in T, I would have to do something. Because I've said nothing. You should assume that x can appear. Right? It's to the right of the magic binding dot. So all bets are on. Right. I'll write some end boxes. Okay, in fact, I'm just going to throw this piece of paper away because it's full of nonsense. I'm tired. I got up horribly early this morning. Right. We're going to be checking types. And we're going to be synthesizing types. Okay. Now, thing I haven't emphasized yet, because in the simply typed case, it was trivial. Remember I said that an input is a signal that goes from client to server, but it's a citizen, right? A citizen is a signal whose sender is its guarantor. And back in simply typed land, all our inputs and outputs were types, and types were automatically well formed just by syntax. That ain't so anymore. So now we have to say, what is the guarantee about an input? So if there is an input, we need to give a precondition in which that input is the subject to say, what is the promise that the sender of this signal must be making? So I'm going to write a set of curly braces here, because Tony Hoare's a friend of mine. And I'm going to insist that there's a precondition that T is accepted by star. Star is the type of types. And I'm even going to write an empty set of curly braces there. I mean, there are no outputs, so there's nothing to have a post condition about. Likewise, I'm going to write empty curly braces there. And a post condition that the S, the type which is synthesized, that's being sent by the server to the client. It's the server's job to make sure that's a type. And now we're actually judging judgments and ruling rules. When you write down our typing rule, You aren't just making any old shit up. You actually have a proof obligation that the thing makes the slightest bit of sense. So we're going to have to work our way, as we work our way around the rules, just checking that we're in a position to justify the preconditions and postconditions that go with the judgment forms we're working with. Okay? Let's have an axiom. Because, you know, it's time we went to hell. Yes? Yeah, the black one. So the black ones, and I'm just going to do this in black and white now. The subjects. So I'll put a red box around the subjects. The subjects the sender makes no promise about, right? The whole point is that the judgment itself is the guarantee we're hoping to end up with about the subject. However, for the inputs, the sender must justify that it's a reasonable question. For outputs, it's the client just must promise this, right? So it's garbage in, garbage out. So client promises that checked types really are types. Server promises that synthesized types really are types. And you'll see, well, okay, it's one of those things. If you're not used to this sort of thing, you won't notice that it's all got simpler. And if you are used to it, you'll get the screaming heebie-jeebies. Right, let's go to hell. Right, we're dead. But notice that well, we're just assuming type is a type. We're allowed to assume type is a type. So there's actually nothing to check for this rule. But this rule will allow us to check a bunch of other things. How do we check that a pi type is a pi type? So this is a dependent function type. The x that stands for the input may appear in the t, the type of the output. Well, we better check that S is a type. And to ask whether S is a type, I have to promise that star is a type. But thank goodness, type's a type. Great. So now I notice, now that S is a type, it's changed status. It used to be a subject, but S has, by this premise, become a citizen. So I'm allowed to create a hypothetical judgment and check that T is a type. So that's, I'm getting paid back immediately for having done some work. The citizenship status of S being established, I can subsequently use it as an input. Context extensions are morally inputs. Okay. So one thing I haven't mentioned so far is that the scoping rules for subjects as opposed to citizens are rather subtle. So in particular, patterns in a subject bind variables which must be used linearly in the premises of the rule. So here I'm obliged, if I'm checking if pi x in ST is the subject of the conclusion, I have to check each of S and T exactly once as the subject in the premises of these rules. So here, S is being checked. Here, T is being checked. And this S is not, it is the citizen that I got by checking this subject. So any use as a citizen has to come in time and space after the single use site as a subject. And why this is important will show up in several different ways. But one thing I'm making sure of, one thing we don't do in this system is any kind of papers, please nonsense. Once something has been made a citizen, it must never, ever again be subjected to scrutiny by a typing judgment. Nothing, things do not move from citizens back to being subjects. And that will turn out to be absolutely crucial in the meta theory. Let's check a function. Right. What do we know? We know that pi x in st is a type. We are promised that by whoever asked us to check this function. Correspondingly, we are allowed to extend the context with little x in type big S, right? Because this can only have come from here, more or less. So we can, by inversion, deduce that big S must have been a type for the whole pi type to be a type. And likewise, I know that big T is a type in the scope of such an X, and now I can check little t. Okay. You will not be surprised that if I want to check some embedded little e, I synthesize some type for it, and then I check that they agree. And once again, I'm going to say that this thing here, S equals T, is it could be lots of things, but today it's on the nose syntactic equality up to alpha conversion. And of course, nothing's ever up to alpha conversion. In real life, we use nameless representations so that we get a canonical representative of an alpha equivalence class. Now, if you're familiar with type theory, you might be thinking there's something missing, namely that these ought to be equal up to some more interesting notion of computation. And you're right, it will reappear in a moment. Okay, but let's truck on the other side with application. Well, let's do application. Trying to figure out the type of an application. We ask for the type of the function, and we pattern match it against being a pi type. So whoever synthesized this type for us is promising us that this is a type, and correspondingly by inversion, we know that S and T make sense. So we're now entitled to check that big S is little s. Oh, I've just realized something. I should have done radicals first. I'm going to hold this rule and do radicals instead, because I need radicals. How do we synthesize a type for a radical? Well, now we've got a little bit of work to do. We have to check that the proposed type is indeed a type. And once we've done that, we can check that the type accepts the term, and then we can give back the type for the whole thing. So once again, you're seeing subjects becoming citizens and being immediately used as such. Okay, thank goodness for that. We've now got radicals, because what type do I want to give back for this function, for this application? Right, I want to give back t instantiated. I've got to instantiate x. Remember, type of dependent function type of output depends on value of input. So I'm going to substitute x by radicalized little s. And I can't just substitute little s for the same reason as before. I have to radicalize the type. And you'll notice that it's just as well this exists, right? If I didn't have radicals, I would have to explain how to substitute little s for little x in a way which didn't leave any beta redexes, because my syntax would contain only normal forms. So even in order to define what the typing rules would be, I would need some effective notion of hereditary substitution. And what we know from this type theory, that because it's inconsistent, there is no way to define such a notion of hereditary substitution. Right? I mean, not only does hereditary substitution, would the substitution only work for well-typed things, right? Here, it doesn't even work for well-typed things, right? If we're trying to normalize away anything that looks like a redex, we haven't a prayer in this inconsistent calculus. So thank goodness for radicals, because it allows us to go slowly. They allow us to go slowly. Okay, so, yeah.
So, that in the rule you just wrote for function application, we know that T is a type because it's been guaranteed by F. How do we know that T is substituted S?
Because these systems are stable under substitution by construction. Yeah, so all I need to do is check that this radical actually has type S, which it does, because we know S is a type because this function type is a type, and we know big S accepts little s, so this radical would synthesize at type big S. Okay. There are two rules missing, and also missing is any notion of computation. And you can see, we're just substituting radicals for variables here. And that means it's possible for us to create a redex. So we ought to be type checking up at least to computation. So here's the deal. You don't actually really get much of a choice about this. The thing about citizens is that they compute. Actually, they just compute whenever they feel like, or whenever you feel like. So there's a rule that says if you're checking a type, you're allowed to pre-compute the type. Yeah? So the type can compute a little bit in advance. That tells you something, by the way, about the language of patterns. When you're matching, right, when you're writing down patterns for citizens, those citizens are dangerously computational. So you better make sure that your patterns only mention canonical constructors, because anything else could compute away, right? We don't want any, I think our Doctor Who reference is possibly safe. We don't want any weeping angels. It should not be the case that that you have to be careful not to blink, right? You know, we're not going to write down anything which, if you blinked, could compute away, right? We're not, yeah. Once something has got as far as being a pi type, no amount of additional computation will ever make it stop being a pi type. So that's important, yeah?
So given that the top part of the rule here has multiple matches, how do we interpret this rule now?
Non-deterministically.
Okay.
It computes. I mean, so this is no longer entirely syntax directed. Basically, citizens can compute whenever you feel like in any way that's allowed by the reduction rule. And of course, the other rule says if we synthesize a type, we're allowed to post-compute that type and give back a slightly more computed type. And that is what allows us here to do conversion checking up to equality. This also separates something that's terribly important, by the way, which is that you notice that computation only goes forwards, and that's just as well because computation is extremely difficult to do backwards. So what basically happens, that these two rules allow us to compute S and T as much as we like before checking that they are exactly syntactically equal. So as long as computation is confluent, forwards computation is enough. You also note that, and this is absolutely traditional, you don't need to do any backwards computation to make to turn a type into a canonical type, right? So if you want a type to be a function type, forwards computation is enough to make that happen. So we clearly separate which things are done by pattern matching against canonical types and which things are done by full-on equality checking. These are separate. Okay, it's probably time I wound up. What was the things I forgot to say? Oh, something terribly important I wanted to say, which is that notice that this thing here, where I do a substitution, is in the output of a conclusion. So that's to say, it's a meta expression. And here, there's a crucial difference between patterns and expressions. You are allowed to do a substitution in a meta expression. You are not allowed to write a substitution in a meta pattern. The reason for that is that substitutions are very easy to do forwards, but very difficult to do backwards. So let me kick to death a thing. Once upon a time, people wrote rules like this to synthesize the type of a dependent pair. First of all, you synthesize the type of the first component, and then, well, and here's the tricky part. I mean, already we're screaming and then you synthesize the type of the second component and then magically unsubstitute it to get a dependent pair type. Right. I'm hoping that one thing you have learned this morning is to look at this rule and instantly see it's bullshit. There is no way to synthesize a generic dependent pair type from one instance of the pair, right? If I give you the number 3 and a vector that happens to have 3 elements, that might be suggestive of a number and a vector of that length, but there's actually any number of types that thing could have. And, you know, so we can't expect to invert a substitution uniquely to figure out the general pattern of dependency from a specific instance of it. So this is, I mean, in all the rules about dependent type theory, which have dependent pairs in, the official rules have all sorts of funny little extra type annotations on the pairs. And now we've actually got a discipline which explains why this is just nonsense in the first place. We're writing an expression in a pattern position. Right. Of course, we can have a checking rule. Yep. So I'll just finish here because this rule's allowed. And you can see no extra type annotations are necessary. Whereas I assure you in every system that implements dependent pairs that we currently use, like well, certainly in Coq, I believe also in Agda, those annotations are actually going to be present. Maybe not in Agda, but certainly in Coq, causing massive exponential blow up of terms. There we are. Good place to stop for now. Let's enjoy some caffeinated beverages or not, as you see fit. Sure.